today we're going to talk about work, and we're going to talk about the fact that work is actually a scalar quantity. Okay, so if we look at work, we're going to start off with the formula. So work is basically defined as the product of the force, okay, that's acting on a body times its displacement. Okay, and actually I'm going to correct that to the distance that the force actually travels. And I'm going to talk to you about why I changed that word from displacement to distance. Okay, if we look at the formula for work, work is basically defined as the force, which is a vector quantity, times, okay, the actual distance that the object travels. And I'm going to actually add in here the angle between the two. Okay, so if we're talking about anything in terms of work, we're talking about the amount of force that an object is going to have applied to it in order to move it a set distance. And the angle at which we put that force down onto the object is going to help figure out what the displacement is. Okay, so work is measured in joules here, right? Force is measured in newtons. Displacement is measured in meters. And then you know what your angles are measured in. So it makes sense that 1 joule is going to be equal to 1 Newton meter, right? You may or may not remember that from last year when we talked about work being done, right? And then we talked about power and things like that. So we're going to get to power in a little bit. But I want to talk about this actual formula first, okay? And I actually want to hit on the idea of the angle here because there's more than one type of angle at play here, okay? So if we keep looking at, the different types of angles out there, all right? So if we look at the angles, so angles involved in work. There's a few different kinds, all right? I'm going to use some diagrams and just some arrows to show you the force versus the displacement, okay? To kind of help you get a mental picture of what's involved here. So the first type of work that we can have is known as maximum work, okay? Max work basically implies that theta is going to be equal to 0 degrees. And what we mean by that is that if I have an object here, right, on my surface, and I want that object to go in this direction, okay? I want it to go from its start point to its end point here, okay? It is going to get displaced this length, all right? In order for that to have the biggest impact possible, I want there to be no degrees of separation between the force that I'm applying and the actual plane of the distance. And what I mean by that is I mean that the force, all right, and actually I'm going to erase that and put my forces in green, okay? So my force here is being applied basically in a horizontal forward motion, and my distance, which I'm going to put in red, is following that exact same plane. And this implies that there's 0 degrees in between the two. Okay? This is going to give you the biggest bang for your buck, so to speak. All right? So that's max work. Unfortunately, I mean, that's what we strive for, but it doesn't always happen. Okay, and if we look at that formula again, if we go back to that formula and we say that work is going to be equal to the force times the displacement times the cos of theta, right? If I have 0 degrees, what is the cos of 0 degrees? The cos of 0 degrees is 1. So this basically is that highest value that you can get. This is where we only have the force to contend with and we only have the displacement. That's the best it gets. Okay? The second type of work that we actually have is the complete opposite of that. All right? It's known as zero work. So zero work implies that theta is going to be equal to 90 degrees. So this is a bit counterintuitive. Okay, so again, here's my surface. All right, here's my box that I'm going to try to move. I want that box to go from xi to xf. So I do want my box to go this way. But if I'm going to apply a 90-degree force to the surface here, that implies that my force is going to go straight down. Okay? If I'm pushing straight down on something, is it going to move this way? No, it is not. All right? This is like me trying to, make a box go forward, and instead I sit on the box. All that force is going down on the box. The box is most definitely not going to move forward. All right? And if we actually end up working this out, okay, we look at our formula again. We see work is going to be equal to the force times the displacement times cos of, 90 degrees. Right? 90 degrees instead of 0. So if you cos 90 degrees, you get 0. Remember this from all of our vector work, right? The cos of something in the y does not have an x value, okay? So if I look at this and I work this out, work ends up being equal to F delta S times 0. So that means that no work ends up being done, okay? Because of that perpendicular angle. All right. Now we're going to get into where the vast majority of work ends up being done. And this is known as effective work. Okay, so effective work, you guessed it, is somewhere in between those two opposite end types of work. So max work and zero work. Effective work is somewhere in between. So we say that effective work is, the theta is somewhere between 0. It's greater than or equal to, well, I would even say it's greater than 0. I would actually argue that it's greater than 0. And it has to be less than 90. Okay, so it's somewhere in the middle. All right, and I'm going to draw this out to show you what I mean here. Okay, an example might be, here's my surface. Okay, so there's my box. Where do you think I want it to go? I want to go from here to here. So I want to go in this direction. But pretend this is a shopping cart. When you're actually pushing a shopping cart, what you're actually doing is you're giving it an actual force. That force ends up having an x component and a y component, right? So that force is going to have an actual x component and it's going to have a y component, right? So it's somewhere in between. So this is where we're going to get a value of anywhere with that cos, we're going to get a value of anywhere between 0 and 1. So it's not the maximum amount of work it can be, but it's better than nothing. Okay? And then finally, which is a little bit counterintuitive, is the idea of resistive work. So resistive work, I really don't think we see too often. So resistive work is basically when your angle ends up being somewhere in between, okay, the opposite of where you want to go. So in this case, we have our surface, all right, and then the force is actually being applied anywhere between, so I would say anywhere between, if we apply our force like so, in this direction, I still want xi and xf, but is that actually going to happen? No, it doesn't happen. I end up actually getting backwards motion. I don't end up getting forwards motion because of that negative angle between the force being applied and the actual displacement that I want. Okay? So these are the the 4 types of forces that kind of are angles between the forces that end up impacting work. So I'm actually going to show you an example now, which is in your notes. We're going to actually look at example B. In this case, it says a person is pulling a crate with a drawbar pull. So it's giving you a pull of 60 newtons of force at 25 degrees. Okay, the displacement of the crate is defined by 50 meters at 0 degrees. So the problem has to do, so I've written down the actual problem. This problem is basically 4 different points. It wants to know what's going on, and I've said it a million times, when in doubt, draw it out. You should always have a little sketch of what's going on. So here they're asking us to draw a free body diagram. Okay, we've done these so many times. So I'm going to actually get down here and draw my free body diagram. I'm going to state my axis as being positive x and positive y. So I've got my surface here, right? I've got my box. I know that I have a normal force going up, and I know that I have the force of gravity going down. Okay, these forces actually should be equal, pardon my drawing, and I know that I have an applied force that's being placed on the object, okay, at 25 degrees. So this is the force here that's actually being applied. Here is my FA. And you'll notice that it's 25 degrees from the actual x-axis. Okay, there's my theta. All right. I also know that I have a displacement here. Okay, so here's my delta x or delta s. I suppose I'll stick with the formula. Means the same thing. Okay, and I know what that value is. So this is a pretty good idea of all the forces that are at play here. So which of these forces are doing the work? Well, we know that the object is moving, okay, in a horizontal manner. Therefore, we don't really care about our actual y forces. Okay, so the only force that is actually doing any of the work here is the x component of that actual applied force. Okay, this guy right here is the only one doing any of the work. Okay, then we've got to do some calculations. So we're asking to calculate the actual magnitude of the effective force. So the effective force is basically the force that's at play here. All right, we know, if we look at C here, we know that EFF, so effective force, is going to basically be equal to the force times the cos, or the angle of the force, right? The cos of the theta. So in this case, we've got 60 newtons times the cos of 25 degrees. So that ends up giving us a number of 54.4 newtons worth of effective force. So once I have that actual force, okay, I can calculate the amount of work required. All right, so what we did here was we actually broke the problem down. We could have very easily just shoved all of this in one equation. So basically work being equal to F times the displacement times the cos of the angle. We could have done that, but they asked us, they actually broke it down here where they asked us to figure out the angle at play in the previous question. So that's why we end up already having that incorporated. The cos is already incorporated in our force here. So we've got our force value, which is 54.4 newtons, and we're multiplying that by our displacement, which is 50 meters. Okay, and that gives us 2,000, I believe, 720 joules of work being done. So that's how we do this. Okay.